Hi everyone, this is the Lab 10 video presentation on water resources, including the hydrologic cycle. So, if you're like me and you grew up in Wisconsin, you grew up around so much fresh water that most of the world really doesn't have access to. Here in Wisconsin, we have a number of uh, rivers, uh, many lakes. We have the Great Lakes, of course, Lake Michigan and Lake Superior, which is a huge amount of the available surface fresh water. Even on when you think about all of the surface fresh water for the entire world, a lot of it is here in the Great Lakes region. But when we think about water resources and the hydrologic cycle, the key word there is cycle. Water is always changing states, like we've already talked about quite a bit in some of the early labs this semester. So it's changing states and it's cycling through the world from the air to the ground, even. So some of the state changes, of course, we should know condensation and precipitation, evaporation and transpiration. We're going to talk a lot about here this lab for the water cycle because that's really important to understand how much available water we have and how much we use or might be lost from our reservoirs, say. And there's water storage too that you need to understand. And water storage could just be a place that water is locked up for some time, such as in glaciers, in mountains, or in the North or South Poles. For we haven't had the glaciers unit yet, but that's just a big chunk of ice you should all be a little familiar with. And then, of course, the traditional water storage places like lakes, aquifers, which are, think of them as underwater lakes. So water stored is stored in those sorts of areas for some amount of time, but it always cycles back in to the greater hydrologic cycle of the Earth. And uh, we should really start with understanding how much water there is on Earth. So these numbers here on the slide are in cubic miles, which is just an insane amount of water. But take a look at the orders of magnitude here. So the oceans, which are of course salt water. So for us humans, it's pretty much locked up there. It's really expensive to desalinate water, but the oceans, contain 300 million cubic miles of water, whereas the next largest storage area as ice, 6 million. So that's a pretty big gap there. So that was ice, glaciers, and polar ice caps. And then the next one would be groundwater, 2 million. That is what a lot of most parts of the world rely on for their municipal sources of water or for irrigation. It's usually pumped out of the ground. And humans have been doing that for thousands of years. But you should just take a glance here at all of the different ways that water cycles through and how much it does. Notice that there's quite a bit of evaporation coming from the oceans and from land. But there's also a lot of precipitation too. So that's rain or snow falling back into the oceans or on land. So the takeaway here is that there's a lot of water stored in the oceans and ice and groundwater, but there's also quite a bit of flux between all these different areas and sources each year. So now that we can appreciate that Earth is really a water planet with a few continents scattered around that we all live our lives on, let's talk about whether that's salt or fresh water. So most of that water on the earth is salt water, saline. 97%. That is just so much. And the rest of it is fresh water. That's only 3% of all the water on the earth. But that's still quite a bit. And if we break that down further, like we already said, most of that fresh water is in ice caps and glaciers. But the next biggest chunk would be groundwater. And here is where we start to get into the surface water that we might be most familiar with in Milwaukee, lakes, and other sources of surface fresh water. So this isn't crucial to your understanding to do the lab assignment, but I think it is important to put things in perspective, just how small of a fraction surface water is, and even larger than that, just how small the freshwater supply is on the earth. So it's really precious, it has value. It has so much value. Water does to our society and life on land, and even in water. So now let's move on. Let's talk about the water table. So the water table is related to the groundwater supply mostly, but it also the water table can also be, it can cause spring-fed lakes and ponds to form as well when the water table might be actually above the ground level at a certain point. So this diagram does a pretty good job at showing how the water table is not just one perfectly flat depth at which you'll start to hit saturated water or saturated soil, but the water table might somewhat follow the surface of the ground. It's not always at the same depth. It depends on a lot of things, like slope, elevation, soil type, or how much water there is, climate, things like that. And what's really the definition of the water table? Well, it's the level at which everything below, all the soil below, will be completely saturated with water. So there's very little air down there, and all of the pores are filled with water. And this is due to the fact that gravity is always pulling water down. So water might fall as rain on the surface, but it seeps down and it infiltrates through the soil to replenish the water table. And infiltration, of course, is basically water seeping down through the soil. And its infiltration rate varies based on the size of particles of the soil, whether it's sandy or clay. Clay is really small particle size. Sand is much larger. And we can think of that as gravel too, gravel would be very, very large particle size and have lots of space between those particles. So porosity was the space between particles of soil or rock or whatever substrate we're talking about. And the permeability is, think of that like a membrane. It allows basically how much water is allowed through. That's not going to be super critical to the lab today, but just wanted to throw that term out there, permeability. So it does affect the infiltration rate. And it's actually pretty straightforward to measure infiltration rate if you wanted to. This YouTube video here I'm going to play does a pretty good job at showing the relative infiltration rates of different substrates. So here we're starting with rocks. There's lots of pore space in between them. You can basically see that, the gaps between the rocks, that would be the pores. Now we have slightly smaller rocks. There's less pore space, and there's a uh, a higher infiltration rate. So it takes water a longer time to work its way through these smaller particles. Here's another substrate, sand. Still pretty quick. The same amount of water takes longer than the two previous media. Okay, so that was almost over 30 seconds. Now, I think you get the point here that the smaller the particles, or whatever it is, rocks or soil, the longer it takes for water to infiltrate through. Now, this has huge implications for like the water table, say, or the amount of available water, or the amount of runoff that could occur. Because if water takes a longer time to infiltrate through, then it's sitting on the surface longer. And if the land isn't perfectly level, there is going to be more runoff downhill. All right, so we're not going to watch the soil drain all the way through, but you get the point. So now I've already said that the water table and basically available water in general is related to weather and climate. So if we look at an entire year, of course, different places are going to have different amount of rainfall. So like the desert here this is taken from the textbook, I believe. And here, this desert climate, there's mostly greater evaporation than there is precipitation because there's very little rain. And there's lots of evaporation because it's really hot and it's very dry. So it's easy for water to change from liquid to a gas. Now, other climates, such as the tropical rainforest here, number 10, you see most of the year it's actually in the blue, which means that there's greater precipitation than there is evaporation. So basically there's a water surplus. And you see here that the timing of when there's a more supply or more demand varies based on the climate. Here in Wisconsin, we have a pretty mild climate. We have relatively wet summers, mild winters. Now, some winters might not feel like that when we get hit with a foot of snow, but compared to other climates, Wisconsin is pretty mild and generally mellow throughout the year. Places on the West Coast, like California, Oregon, Washington, that are to the west of the Rocky Mountains, would have actually a very wet winter, but a drier summer. So don't assume that every place on the same latitude would have the same types of periods of supply and demand with respects to water. But that climate is complex, of course, and there can be places of drought or surplus water just based on different geographic location. So I just mentioned places like west of the Rocky Mountains. Here in LA, maybe some of you have heard or read about this. It kind of went viral a few years ago when the city of LA did this to the reservoir. But basically, they had issues with high evaporation rates. So what did they do? They're creating a physical barrier, and they dumped all these 96 million shade balls into the Los Angeles reservoir to create a barrier, a physical barrier, to prevent evaporation off of the surface. Because it's so hot and so dry, and water just naturally wants to turn back into a gas very readily. I did follow up, and it seems like it's working. There were some unintended consequences and critiques of this method, but in general, it has reduced the amount of evaporation that this reservoir has had. You can follow this link if you want to see more about this, but it's kind of mesmerizing to watch these balls flow into the water. So you can follow the link in the slides if you'd like, if you want to learn more about that. But the point here is that places like LA have issues with water supply because if you store water on the surface, like in a reservoir to catch from rainwater, say, there's so much evaporation that it's hard to keep it there. The water just doesn't want to stay. So what do? Well, they have to draw up from the ground, and that comes with its consequences too, because with so many people living in areas that are basically desert, or even in Wisconsin, there's issues with groundwater. You'll read a little bit about in the lab this week that there's only so much water that can replenish the groundwater supplies, these aquifers, and it takes time for that to happen. That doesn't just happen from one big rainstorm. It takes a long time. So now I'd like to talk a little bit about a case study that is going to be in the first section of the lab. So if you follow along with what I say here, you'll basically get one free answer in the lab this week. And it asks what would be two implications for the water cycle, two effects that there might be from certain events. This event, that the first one is going to be deforestation. What does that mean for the water table? And there's a lot of ways you could tackle that question. I'm going to answer it with knowledge from the rainforest in South America. The Amazon rainforest has really high transpiration rate. And to explain what transpiration is, it's very similar to the word evaporation. And evaporation is the phase change of water from liquid to a gas. And transpiration is basically the same phase change from liquid to a gas, but it's facilitated by plants. So trees and all plants draw liquid water up through their roots, through their stems, and out through their leaves. But when it leaves their leaves, it leaves as a gas. So there's a phase change that occurs there. It's pretty complex, but just understand that transpiration is basically facilitated by plants. So plants, and there's so many plants in the rainforest, especially places like the Amazon, that plants actually and trees pump water into the air because there's so many plants per area that they act as a water pump, pumping gaseous water into the air, water vapor. So when rainforest might be cleared and give way to pasture land for cattle, say, or for development, there will be a lot less evapotranspiration or transpiration from plants. So there's going to be less water in the air, a little bit. And given enough deforestation, that can make a pretty big impact. Another thing that would happen to the water cycle might be due to runoff. So if you imagine a rainfall event, it rains a lot in the Amazon, and the Amazon has lots of trees, of course, very tall trees, and they sometimes have both secondary or tertiary canopies, meaning that there's just different layers of trees. There's some emergent, really tall, like 300 feet plus trees, and then there's some underneath. So if you imagine when it's raining, water droplets are falling down. They might hit leaves, and then say it only rains for like an hour, but the leaves might still be dripping water for 3 hours. So that time of precipitation felt by the ground might be spread out over a longer distance. And if we bring that back to the infiltration rates, the infiltration rate for the surface or the soil rather, infiltration rate is basically fixed. Okay, so there's based on soil type, like whether it's sandy or clay or whatever, that's basically a fixed number. There's only so much water that can infiltrate through the ground per unit time. And if there's anything more, like if it's raining really hard, well, then that water just collects on the surface and it runs downhill. And there could be really high runoff or less infiltration rate through the ground, less infiltration over time. So when there's deforestation event, there could be more runoff and less infiltration rate and less replenishing the groundwater supply. So I'll work through that same sort of mental process to figure out what the other implications might be that would be in section 1 of the lab assignment for this week. I think you actually have 3 weeks to do that. It's actually due after Thanksgiving, Lab 10. Especially think about water storage areas, like when global temperatures change. There might be, if global temperatures increase, what might that mean for the water that's stored as ice? Remember, that was a pretty big fraction of all the fresh water stored in glaciers and the poles, North and South poles. Also think about what happens for development. Does concrete allow for infiltration? Generally, no. So for the lab assignment, Lab 10, in section 3, you are asked to follow the PDF documents that are put out by the Wisconsin DNR. Every year they do a water use report for the state based off of things like how much municipal water is drawn by each city or by agriculture sector or by the power generation sector, which is a pretty big section. And we're going to ask a couple questions about a contentious issue actually in Wisconsin that is still up in some of the courts, whether there should be a limit on high capacity wells. Now we're going to not ask what you feel about the topic, but based on the reports, whether it seems like it's a sustainable practice or not. A high capacity well is, if you've ever driven through the central parts of the state, like the central sands where it's really flat and they have these lots of agriculture, but it requires irrigation. The soil there is very sandy and flat, and basically these rotary irrigation platforms draw up water from the ground because that's like the only place they can, and they basically spray it on crops to irrigate. So that's what we're talking about when we say high capacity wells. It'll make more sense when you read the water resources report. And in section 4, we're going to be talking about swimming pools in Arizona and what the precipitation versus evaporation potentials could be. So when you work through section 3 and 4, think of this image on the right for the high capacity wells. That's what we're talking about. And on the left, bottom left, for a swimming pool in the desert. All right. If you have any questions with Lab 10, feel free, of course, to email us, or we can meet through Microsoft Teams as usual. And have a great Thanksgiving break. Whether you go home or not, just enjoy your time off and time with family if you see them. Stay safe. Good luck.